Hello, this is QMG, the Quantum Guy, bringing you more news for you. Look at the title of this one. Physicists watch quantum particles tunnel through solid barriers. Here's what they found. Uh, it's, it sounds like the particles made a hole through the wall in order to get to the other side, but you'll see it's very interesting. This paper does a very good job of showing you experiments that I think are going to become part of textbooks very soon because the experiments are very well crafted. So let's begin looking at the picture. This is not, I don't think this is a good representation of quantum tunneling, but it's a nice picture to have in this article. Let's move on to the article right here. Okay, I'm going to start right here. Okay, you can see it. The quantum world is a pretty wild one where the seemingly impossible happens all the time. Teensy objects separated by miles are tied to one another, and particles can even be in two places at once. But one of the most perplexing quantum superpowers is the movement of particles through seemingly impenetrable barriers. So this paragraph, okay, showing you what I've been showing you already with the IBM Quantum Experience platform, which is an actual quantum computer that you've been watching in this channel live. This is showing you the entanglement, the superposition, and many other weird things that happen with quantum systems. But according to this article, and this is just an opinion, that it is that the most that is the tunneling, this phenomenon that we're going to be discussing right now, is the most perplexing. And to be honest with you, I don't think it's the most perplexing. Okay, it is perplexing if you think in terms of particles. It makes more sense when you think in terms of waves. I will show you. And I think that's where the confusion comes when it comes to this concept of tunneling. Let's keep reading. Now a team of physicists have devised a simple way to measure the duration of this bizarre phenomenon called quantum tunneling. And they figure out how long the tunneling takes from start to finish. The moment a particle enters the barrier, tunnels through, and comes out on the other side. They reported on July 22 in the journal Nature. And there's a nice article written in Scientific American about this one that is a little more extensive and gives you much more details. This one is a little more concise and gets to the point of the most important things that the article covers. Let's go to the next one. Quantum tunneling is a phenomenon where an atom or subatomic particle can appear on the opposite side of the barrier that should be impossible for the particle to penetrate. It is as if you were walking and encounter a 10-foot wall, 10-foot tall, 3 meters, wall extending as far as the eye can see. Without a ladder or Spider-Man climbing skills, the wall would make it impossible for you to continue. I think this is where the confusion comes into place. It tries to describe the phenomenon of quantum tunneling, but notice how this paragraph puts it all in terms of a particle. Of course, if you have a ball and you throw it on a wall, what is going to happen? It's going to bounce back, right? It would be weird if it appeared on the other side. That is the wrong analogy. I would like to claim that it is easier when you start thinking in terms of waves because waves can go through walls, right? And the more thick the wall is, the less sound or intensity you are going to hear on the other side. And I think that's a better analogy. So this is a very, I think, bad example because it doesn't help to understand the concept of tunneling. It just confuses completely, right? Remember, when you deal with quantum systems, sometimes you have to decide whether you want to start thinking in terms of waves or particles. I think in this case, it's easier to think in terms of waves rather than particles, and that's what makes it a little more confusing. However, in the quantum world, it is rare but possible for an atom or an electron to simply appear on the other side, as if as if a tunnel had been dug through the wall. Quantum tunneling is one of the most puzzling of quantum phenomena, said study co-author Ephraim Steinberg, co-director of the Quantum Information Science Program at Canadian Institute for Advanced Research. And it is fantastic that we are now able to actually study in this way. Okay, so it is exciting to be able to study this one. Uh, in my opinion, my personal opinion, I think entanglement it's more bizarre than the quantum tunneling because you will see, I think tunneling can be explained in terms of waves. At least you could mimic quantum tunneling by means of wave phenomenon that we are familiar with. Let's keep moving. All right, there you go. All right, so quantum tunneling is not new to physicists. It forms the basis of many modern technologies such as electronic chips called diodes, which allow for the movement of electricity through a circuit in one direction but not the other. Scanning tunneling microscope, STM, also use tunneling to literally show individual atoms on the surface of a solid. Shortly after the first STM was invented, researchers at IBM reported using the device to spell out the letters IBM using 32 xenon atoms on a nickel substrate. Okay, so yeah, the uses of tunneling in the industry it's already there, and I can tell you about scanning with tunneling microscopes. It allows you to see how rugged a surface is. It's kind of like when you speak. Okay, you can determine by the reflection how close something is, and also you can tell the thickness of something, right, by how much goes through and how much comes back, right? If a lot goes through, well, then it's a very thin wall. If nothing comes in, then that means a very thick wall. That's a very rough description of wave phenomenon that helps you determine how thick a wall, and that's more or less okay what these devices do. Okay, and again, my my opinion for this article will is that it's easier to think in terms of waves. Thinking in terms of particle just makes it confusing for anyone reading the article that is not familiar with quantum mechanics. While the laws of quantum mechanics allow for quantum tunneling, researchers still don't know exactly what happens while a subatomic particle is undergoing the tunneling process. Indeed, some researchers thought that the particles appears instantaneously on the other side of the barrier, as if instantaneously teleported there. Okay, now this is where I disagree with the article. They use the word teleported. We're not teleporting anything, okay? We're transporting something, right? Teleporting, let me just mention briefly, is a phenomenon in quantum mechanics where a quantum system can appear on the in another place without transmission of mass or energy, right? What we're doing here is tunneling, and here we are transmitting mass from one place to the other, right? We start on one side of the wall, and then it comes on, and then it appears on the other side. And the point of this paper is to measure the time that it takes to stay inside. And what this article is saying is that that time was not easily interpretable from the mechanism, the formalism that we have in quantum mechanics, which is, in a way, you could say something like that. So at least this experiment helps to clarify that part. It helps to clarify how long it would take to go through given this particular experiment. Okay, there were experiments that they did before where it was not clear whether whether or not they actually measure that time, right? Remember, when you're using waves, it's kind of hard to know where you start, right? And when it comes on the others, and when it comes out on the other side, right? It's because a wave is distributed as opposed to a particle that is very localized. So that's the tricky part from the previous experiment. This one is better. Let's keep reading. Now you'll see. Researchers had previously tried to measure the amount of time it takes for tunneling to occur with varying results. One of the difficulties in earlier versions of this type of experiment is identifying the moment tunneling starts and stops, right? To simplify the methodology, the researchers used magnets to create a new kind of clock that would tick only while the particle was tunneling. So as I said, particles are hard to know when they start, when they come out on the other side because they are distributed. So this time, to measure the time, they're going to use a magnetic field. And this is where the clever part comes in this experiment. So let's keep reading. Subatomic particles all have magnetic properties, and when magnets are in an external magnetic field, they rotate like spinning top. The amount of rotation, also called precession, depends on how long the particle is bathed in the magnetic field. Knowing that, the Toronto group used a magnetic field to form their barrier. When particles are inside the barrier, they precess. Outside it, they don't. So measuring how long the particles precess told the researchers how long those atoms took to tunnel through the barrier. So here's a better picture. And now for this part, I cheat a little. You can actually think in terms of particles because when you're talking about spin, you kind of have to refer to to the concept of particle. Although I'm going to tell you, you can also think in terms of a spinning wave, okay? But I don't want to make it so complicated like that. So when atoms go through the barrier, the quantums, okay, which are the atoms, they're rotating. So if they are charged, they are like little magnets, right? So you can imagine little magnets coming in, and when they go into the magnetic field, they start wobbling inside, right? They wobble, and by counting the time that it spends wobbling, you can figure out the time that atom spent inside the barrier. So it comes. So there's no wobbling. Then it goes into the magnetic field, starts wobbling, and then it comes on the other side, not wobbling. So this wobbling can be detected, and presumably, according to the experiment, and you can determine how long that particular particle was inside the magnetic field. The experiment is a breathtaking technical achievement, said Drew Alton, physics professor at Augustana University in South Dakota. The researchers prepare approximately 8,000 rubidium atoms, cool them to a billion of a degree above absolute zero. The atoms needed to be this temperature, otherwise they would have moved around randomly at high speeds rather than staying in a small clump. The scientists used a laser to create the magnetic barrier. They focused the laser so that the barrier was 1.3 micrometers, micrometers, right? Microns thick, or the thickness of about 2,500 rubidium atoms. So if you were a foot thick front to back, the barrier would be the equivalent of about half a mile thick. Using another laser, the scientists nudge the rubidium atoms towards the barrier, moving them about 0.15 inches per second, 4 millimeters per second. So this loaded paragraph, what are they saying? Well, they took a bunch of rubidium atoms, exactly 8,000 of them, and they use a laser to push them at the speed of 4 millimeters per second. So I'm going to simulate here 4 millimeters per second. That's more or less 4 millimeters per second. As you can see, it's a visible speed. And then they have to be very cool, right? So remember, in order for something to exhibit the properties that we're looking for, the wave properties, they have to be, the momentum has to be very small. So remember, there's a relationship between the wavelength and the momentum, right? They're inversely proportional to one another. And the barrier was 0.15 inches for, it was 1.3 micrometers. So that's about the size of a very, very small microbe. Okay, let's continue reading. As expected, most of the rubidium atoms bounced off the barrier. However, due to the quantum tunneling, about 3% of the atoms penetrated the barrier and appeared on the other side. Based on the precession of the atoms, it took about 0.6 milliseconds to traverse the barrier. So they got results, right? They have the wave coming in, and the wave went through it. Not all of it went through it, only a small fraction, 3% of that. And all of the other ones got reflected, right? And it took 0.6 milliseconds to traverse the barrier. So that's a good thing to know, right? That's the most important result from this paper. Chad Orzel, an associate professor of physics at Union College in New York, who was not part of the study, applauded the experiment. Their experiment is ingeniously constructed to make it difficult to interpret as anything other than what they say, said Orzel, author of How to Teach Mechanics to Your Dog. It is one of the best examples you'll see of thought experiment made real, he added. Okay, it's a very good experiment. And let me tell you why it's a good experiment. In science, you want to have experiments that could be wrong. You don't just want to be verifying, that are correct, right? And these experiment, they could have been wrong, right? They could have found as before that, the transmission is immediate, right? They could have detected no time. In the other experiments, they work. His experiment seems to be right. Let's keep reading. Experiments exploring quantum tunneling are difficult, and further research is needed to understand the implications of this study. The Toronto group is already considering improvements on their apparatus to not only determine the duration of the tunneling process, but also see if they can learn anything about velocity of the atoms at different points in the barrier. We're working on a new measurement where we make the barrier thicker and then determine the amount of precession at different depths. Steinberg said it will be very interesting to see if the atom's speed is constant or not. Okay, yeah, that's an interesting experiment. And again, it's not clear from the formalism of quantum mechanics exactly what they will obtain, right? So certainly his experiment is making a contribution to have more empirical information about the world. In many interpretations of quantum mechanics, it is impossible, even in principle, to determine a subatomic particle's trajectory. Such a measurement could lead to insights into the confusing world of quantum theory. The quantum world is very different from the world we are familiar with. Experiments like these will help make it a little less mysterious. Now, there are interpretations of quantum mechanics where you could interpret particles as following trajectories, and it is true you wouldn't be able to determine what those trajectories are, but from the point of view of those interpretations, these particles are being arranged by what is called a quantum potential. And it is this quantum potential that gives extra energy to these particles to jump the wall. So it is possible to make that interpretation, but certainly it is not possible to figure out what those trajectories are, right? And certainly this experiment, it's a wonderful contribution. It's I can tell you this is going to be one of those experiments that you see in books very soon. And of course, if they can get more details about the different, if they can get different results as they presented here with different conditions, well, that would be very helpful as well. Well, it was wonderful being here with you again. And of course, like always, for those about to quantum, we salute you and see you next time.